Up until now, we've been focusing our attention on right triangles. However, many of the triangles that we encounter, both in mathematical theory and in real life, are not right triangles. So we're going to begin looking at how we can use our trigonometric functions to understand such triangles. So, in order to do that, we're going to start by looking at a fact known as the Law of Sines, and it's a way of relating the angles and sides within a triangle to one another using the sine function. To see how this works, let's take a triangle here, and let's suppose that it's not a right triangle. Now, when we do this, we have a standard way that we describe the angles and side lengths in it. We will usually denote the three sides, or the three angles rather, as alpha, beta, and gamma, and the lengths of the sides opposite those angles as A, B, and C, respectively. When we do this, we also have as standard that the points, the vertices of the triangle, will be labeled capital A, capital B, and capital C. We've already looked at this a little bit back when we first started talking about solving triangles. And in that case, we were looking at right triangles. And here, we'll use the same terminology to describe solving any angle. So to solve a triangle means to find all six of alpha, beta, gamma, A, B, and C. That is to find the measures of all of the angles and all of the side lengths in the triangle. As we saw before, we need a certain amount of information to get there. Typically, 3 pieces of information. If we can know 3 of these pieces of data, we can often determine the others, or at least we'll be able to narrow down the possibilities for the others restrictively. So let's look at this triangle and say, let's suppose that we wanted to understand the relationships between alpha, beta, gamma, and A, B, and C. One way that we could do that would be the following. Let's see what happens when we draw a line straight down from C to the side AB. Now, a couple of points here. I have specifically drawn this triangle in such a way that when I bring down this perpendicular line from the point C to the line containing A and B, that its point of intersection right here lies between the points A and B. This doesn't have to happen. In this case, this happened because all of my angles in this triangle are acute. However, if one of your angles is obtuse, that is having an angle measure of more than 90 degrees, then this point might fall somewhere else. You can look in the book for an illustration of how this reasoning we're about to do works when the blue line here doesn't actually intersect the segment AB. The argument is going to go basically the same. Only minor differences are required. Let's give this blue segment length the label H. Now, the reason why I want to do this is because I've now introduced a couple of right triangles and I can start using my trigonometric functions. And in particular, what I want to look at is sine of alpha and sine of beta, because those are the 2 angles that are both in my original triangle and in the right triangles that I've just introduced. So we have that sine of alpha is equal to H over B, and that's just because this triangle AC, let me give it the label D. The triangle ACD is a right triangle. Alpha is one of the angles inside it. The opposite side, within this right triangle has length h, and the hypotenuse has length b. Therefore, sine of alpha is h over b. And I want to rewrite that as h equals b times sine alpha, for reasons that will become clear in a second. Now let's look at sine of beta. That's the other angle that's both in my original triangle and in one of the right triangles I just introduced. Sine of beta will be h over a, which, if we rearrange it, gives us h is equal to a times sine beta. So in this problem, we have that h is equal to b sine alpha and h is equal to a sine beta. Now, of course, that means that those two expressions have to be equal to each other. So b times sine alpha has to equal a times sine beta. Now, this is already interesting. It tells us that there is, in fact, a relationship between alpha, beta, a, and b that we get at using the sines of alpha and beta. But I want to go further and divide both sides by a times b in order to get the expression sine alpha over a equals sine beta over b, which turns out to be an even more useful way of writing things down. So we get some ratios here that are equal. Sine of alpha over a is equal to sine of beta over b. It turns out that if you do the same argument but just switch which points you're looking at, you can also get that sine of gamma, that this ratio is also equal to sine of gamma over c. And so what this tells us is that we've got a bunch of equalities between sines of angles and side lengths of the triangles. This equation is what's known as the law of sines. So the law of sines. If triangle ABC is labeled in the standard way, then sine of alpha over a equals sine of beta over b, which equals sine of gamma over c. And it turns out that we're going to be able to exploit this in order to solve triangles that are not right triangles. So let's see an example. So let's solve triangle ABC if alpha is equal to 36 degrees, beta is equal to 50 degrees, and a is equal to 12. Now, typically when you are going through and solving these problems, it's going to be helpful to keep a sketch around of what's going on. It doesn't have to be super accurate, but it will help. It'll help you keep track of things. So let's see. We've got alpha, which is 36 degrees. We have beta, which is 50 degrees, and we have gamma, which we don't know. We know that A is 12, and that's the side opposite alpha. We have B, which we don't know, and we have C, which we don't know. So we need to figure out gamma, B, and C. Now, there are a couple of different arrangements of the data that you can be given. Now, you always need to be given at least 3 pieces of data between angles and side lengths. Now, in this case, we're given 2 angles and 1 side. This is the easiest collection of data to use. So if we have 2 angles and 1 side, first of all, figuring out the other angle is very easy, and that's because we know that the sum of the interior angles of a triangle is 180 degrees. So let's start off by finding gamma. we know that gamma is 180 degrees minus alpha minus beta. So that's going to be 180 degrees minus 36 degrees minus 50 degrees. And those become 86 degrees. So gamma is actually 94 degrees. So that part's usually pretty easy. When you're given two angles, this process is usually pretty quick. Now, let's figure out the others. Now let's try to figure out what B is. What you want to do is you want to use one of the equations given by the Law of Sines in order to relate the information that you know to the information that you don't know. Now, you'll notice that the Law of Sines up here actually has three equations involved. We've got an equation involving alpha and beta, an equation involving alpha and gamma, and an equation involving beta and gamma. And we only use one of those three equations at a time. So if we're trying to find B, and we're using the Law of Sines, then that means that we're also going to want to include beta. So definitely part of what we're going to use here is that sine of beta over B equals one of our other ratios. And so now we want to think, do we know alpha and A or gamma and C? And of course we know alpha and A. We know that this is sine of alpha over A. Now what's important when you go to set this up is that you need to know three of the four quantities in this expression. We need to know either two of the angles and one of the sides, or both sides and one of the angles. If we know two or more unknown, if there are two or more unknown quantities in the equation, then we're not going to be able to solve it. So if you set up one of these equations and you have two pieces that you don't know, well then you need to go back and try something else because it won't work. In this case, we know that beta is 50, so we get sine of 50 degrees. We don't know B, that's what we're trying to find. Now we know that alpha is 36 degrees, and we know that A is 12. So we get this expression, or this equation rather, that we can solve for B. So if we solve for B, we wind up getting that B is equal to 12 times sine of 50 degrees over sine of 36 degrees. Now, as always, your problems will indicate whether they want you to give an approximate answer and tell you to round to a certain number of decimal places or not. Typically, when solving triangles using the Law of Sines, we'll usually be approximating our answers, because usually the angles involved are not going to be angles that we're familiar with and that we know the values of exactly. So this is something that we can pull out a calculator for. So let's pull out our handy dandy calculator. I check we are in degree mode, which is what we're using here. So let's go ahead and figure out what this B would be. So we get 12 times, oh sorry, that did not do what I wanted. We get 12 times sine of 50, and I do a quick double check that I'm in degree mode because it's easy to forget to do that. So we get 12 times sine of 50 divided by sine of 36 degrees, and we get that B has to be 15.639. I'll go ahead and round it to 3 decimal places here. And so that's how we figure out what that side of the triangle is. So now we are 2/3 of the way done, and that's as easy as it is when it comes to solving for the sides of the triangle. Is just applying this formula. So let's do the same thing with C. Because we're trying to find C, we definitely want sine of gamma over not over gamma, but over c. Now we know sine of gamma, or we know gamma, and so we want to put on the other side here either sine of beta over b or sine of alpha over a. Now, at this point, we do know beta and we have an approximation for b, but we still don't want to use those. Just like when we were solving triangles before, as much as possible, we want to use the original data that was given to us at the beginning of the problem. We want to avoid, for as long as possible, using approximate values that we have worked out during the process of the problem. So, instead of using sine of beta over b, which involves a quantity that we solved for, we'll go ahead and go all the way back to alpha and a because those were what were given to us in the problem. So we have that sine of gamma over c is equal to sine of alpha over a, which means that sine of 94 degrees over c is equal to sine of 36 degrees over 12. Now at this point you may accuse me of hypocrisy because I just said that we weren't supposed to use quantities that we derived in the process of the problem in order to do our later steps, and that is true as much as possible. Now, in this case, we're forced to use gamma, even though gamma wasn't given to us originally in the problem, because that's the only way of getting at the value c using the law of sines. The law of sines only gives us ratios that relate an angle to its opposite side. Therefore, the only way that we're going to be able to figure out what c is by using the gamma that we came up with. So the philosophy of not using the quantities that you've derived for is one that you want to hold on to as long as possible, but sometimes you won't be able to, you'll need to actually use stuff that you derived during the problem. And that's okay. So if we solve this for c, then we'll get c is equal to 12 times sine of 94 degrees over sine of 36 degrees. And so we can go up to our problem, or to our calculator, and in fact just change the 50 to a 94 to get 20.366. So we get that c here is 20.366 approximately, and we have solved our triangle. Now at this point you do want to do a quick sanity check, that is to make sure that the numbers in the problem make sense. A few things that you can check. Unless one of your angles is very, very small, the side lengths of your triangle should all be approximately in the same ballpark. I wouldn't expect to have a side length of 12 and then a side length of 15 and then a side length of 2,000, something like this. There can be quite a bit of variation, but the greater the if there's a huge difference between two sides of the triangle, that means that one of your that means that one of your angle values must be very, very, very small. And so if you don't have that, then you should expect your side lengths to all be approximately in the same ballpark. And to that end also, we can double check in our problem. We always want to make sure that larger sides are opposite larger angles. This is a general principle from geometry that in a triangle, the larger sides are opposite the larger angles. So in this problem, we have that the angle 36 degrees is the smallest angle in the problem, and it's opposite the smallest side. Then the middle angle is 50 degrees, beta, that's opposite the middle length side. The largest is gamma with 94 degrees, and that's opposite the largest side with about 20.366. So everything makes sense here. There are no warning signs, so we probably did everything just fine. Now, this process that I went through holds for basically any situation where you have two angles that you know and one side length. If you ever have a triangle where you know two of the angles and one side length, you can always solve it using the law of sines in the way that we just did. Let's look at some of the other possible arrangements of data that we can have, and look at how we can solve them. Now, there is one other type of data that we can have that the law of sines applies to, but there are some others that we won't be able to do using the law of sines, and we'll need other techniques. Okay, so what we have is if we know angle, angle, and side, we can solve using the law of sines. If we know two angles and a side, then we can solve it using the law of sines. Oh, and we can also solve it if it's of the pattern angle, side, angle. That is, let me illustrate these things here. So angle, angle, side would typically be a situation where you know two angles and then some side that doesn't lie between them. Angle, side, angle would be knowing two angles and the side between them. Both of these can be handled using the law of sines, the way that we just did. Your first step is to figure out what the angle measure of the other angle is, and then go from there. Let's run through a couple more. What if we have angle, angle, angle? Well, this one we cannot solve. And that's because if I only give you the angle measures of a triangle, you don't know what size it is. We know that there are lots of similar triangles, that is, triangles that have all the same angles inside, but have different sizes to them. So we actually can't solve a triangle if all we're given is three angles. Now, if we're given three sides, unfortunately, this is also something that we can't solve using the law of sines. And that's because when we use the law of sines, all the equations that we get always involve two angles and two side lengths. And so if we start with with knowing only the side lengths, then we will always have at least two unknown quantities in our ratio using the law of sines. However, it's going to turn out that this is something we'll be able to solve using the law of cosines. All right, so then next we've got, we considered what happens if we have three angles, three sides, two angles, and so now we can consider what happens if we have two sides. And again, there are two forms of this. We could have side, angle, side, or side, side, angle. So let's suppose that we know an angle and two sides. Unfortunately, once again, this is something that we can't do using the law of sines. Let's see why. Let's label these. If that's alpha, beta, gamma, b, and c, then the law of sines says that sine of alpha over a equals sine of beta over b equals sine of gamma over c. And let me note the parts here that we don't know. We don't know a under this setup where we know two sides and the angle between them. We don't know beta. We do know b, but we don't know beta, and we don't know gamma. And the point again is that if we take any equation of two of these ratios, there are always two unknown quantities. And therefore, we're never going to be able to solve for any one of those quantities. This is another one that we can't solve using the law of sines. This is one that we'll have to handle using the law of cosines in the next section. But then side, side, angle, this is one that we can potentially solve. So this is one where we have two sides and we know an angle. This we can also handle using the law of sines. And that's because we actually do know about an angle and its opposite side. That's what we need to work with. However, there are some things we have to be careful about here. However, we may have 0, 1, or 2 solutions. You may remember from geometry that you had the various congruence theorems, like side, angle, so forth and so on. Well, you may remember that there is no congruence theorem for side angle, and this is basically the reason why, is that if you tell me two sides of a triangle and an angle that doesn't lie between the two, then there could be more than one triangle that satisfies those conditions. So we'll look here at the case where we've got two sides and an angle that doesn't lie between them, and we'll see how we can get more than one solution, or maybe even no solutions at all. All right. So let's see an example. All right. So solve triangle ABC if alpha equals 46 degrees, A equals 7, and B equals 10. All right, so we can draw our triangle to keep track of our things. We've got alpha is 46 degrees, A is equal to 7, B is equal to 10, and we've got beta, gamma, and C over here, which we want to figure out. So we want to use one of our ratios in the law of sines or one of our equations of ratios rather, in order to figure out one of these unknown quantities. Now, in this case, we only know one of the angles, so we can't figure out the third one immediately the way that we did last time. And that means also that the values of gamma and C are totally off limits to us. We don't know the value of gamma or C yet, and therefore we can't use the law of sines in order to access either one of them. We always have to know one of the angle and the opposite side in order to be able to get at it using the law of sines. So what we can do is figure out what's going on with B and beta. So we have that sine of alpha over A is equal to sine of beta over B. So that means that sine of 46 degrees over 7 is equal to sine of beta, which we don't know, over 10. And at this point, we want to solve for beta. And if we solve for beta, then we get that sine of beta is equal to 10 times sine of 46 degrees over 7, and we can go ahead and pull out our calculator in order to get that. So we've got that 10 times sine of 46, I'm in degree mode, divided by 7 is what we want our sine of beta to be, and we get 1.028 approximately. And here's where we see that we've got a problem. We need that sine of beta equals 1.028. But of course that can't ever happen. Sine of an angle can never equal more than 1, and so this means that we have no solution. So that means that there is no possible beta that makes this work. And therefore there is no triangle at all that has the data that we are given at the beginning of the problem. There is no triangle where we've got an angle of 46 degrees, opposite side of 7, and one of the other sides having length 10. It simply can't work. Now, we can know what's going on here, basically. Why is it the case that there are no triangles with such a ratio? Uh, Basically, what's going on here is the following, or we can see it this way. If we try to construct such a triangle and we construct an angle of 46 degrees, and we go out 10, then we're trying to take a side down here and basically have it match up with one of the points on this line, on the base. The problem is that a side of length 7 is simply too short. No matter how we try to put this angle down here, it's never going to reach that lower horizontal line, and so it's actually never possible to get triangle with these side lengths here, because that opposite side of length 7 simply doesn't reach. So this is one of the things that can happen in a side-side angle situation. You might simply have no solution. And the good thing is that when that happens, you're basically told immediately why that is, and it's because, well, the sine of beta here comes out to be more than 1. So let's look at another example. Let's consider this situation. We're trying to solve the triangle ABC, where we've got alpha is 30 degrees, A is 9, and B is 18. And let's go through the same process. And again, we don't need to sketch, but it's often a good idea to. We've got alpha, we've got A, we've got B is 18, 9 is A, there, and then we've got beta and gamma. And just like before, there's only one quantity in here that we can access. The only quantity we have access to is beta here. So we can get that sine of alpha over A is equal to sine of beta over B. Sine of alpha, or alpha is 30 degrees, A is 9, beta we don't know, and B is 18. So, rearranging, we get that sine of beta is equal to 18 times sine of 30 degrees over 9, which is equal to 2 times sine of 30 degrees. But actually, we're familiar with 30 degrees. We know that sine of 30 degrees is actually 1/2, and therefore 2 times sine of 30 degrees is just 1. So that means that sine of beta is equal to 1. Well, that we can figure out exactly what beta is. There's only one value of beta that works here, because the angles in a triangle, of course, must always be between 0 and 180 degrees. The only angle in that range which has a sine of beta is 90. So this, in fact, gives us that beta is a 90-degree angle. And so, in fact, we're looking at a right angle here. So, in fact, we didn't even have to go through we don't have to go through the rest of the process. We don't have to use the law of sines on this, because we know that this is a 30, 60, 90-degree triangle. But we'll go ahead and finish it off just for the sake of practice with the law of sines. Now, once we get that we've got an angle of 90 degrees here, that beta is 90 degrees, we can figure out what the other angle is. We can get that gamma is equal to 180 degrees minus 30 degrees minus 90 degrees to give us 60 degrees. So that's what gamma is. And then to get C, we can use the law of sines again. Now, we don't need to because this is a right triangle, but we can. So we can have sine of alpha over A is equal to sine of gamma over B. That gives us, of course, that sine of 30 degrees over 9 is equal to, oh, sorry, not sine of gamma over b, that's ridiculous. Sine of gamma over c, because c is what we're trying to find. So sine of 30 degrees over 9 equals sine of 60 degrees over c. We solve that for c, we get that c is equal to 9 times sine of 60 degrees over sine of 30 degrees. And we know the values of all these various things. We know that sine of 60 degrees is square root of 3 over 2. We know that sine of 30 degrees is 1/2. When you simplify all that down, we wind up with 9 times the square root of 3. And so in this case, there wasn't even any approximation necessary. And so we get just a single triangle which satisfies these conditions, which happens to be a right triangle. All right, let's look at another example. Let's suppose that we've got that alpha is 33 degrees, A is 7, and B is 10. Now, this one's going to take a little bit more space, so I'm not going to sketch out the diagram yet. We'll do that at the end once we've seen what the algebra tells us. So we want to figure out beta because it's the only thing we have access to. We don't know c or gamma, so we can't figure out either of them yet. So we have that sine of alpha over A is equal to sine of beta over B. This means that sine of 33 degrees over 7 is equal to sine of beta over 10. Solving for sine of beta, we get sine of beta is equal to 10 times sine of 33 degrees over 7, and this we'll want to approximate. So we'll get 10 times sine of 33 degrees over 7, which gives us approximately 0.7781. I'm going to go ahead and keep things at 4 decimal places here throughout the problem. So sine of beta is 0.7781. So what does that mean beta is? Well, here's where we can get some of the strangeness that can occur, or the thing that makes the side-side angle situation different than the others. Because, as we know, there's more than one angle in the unit circle which has a sine of a given number that's less than 1. There's going to be some angle over here which has a sine value of the 0.7781 that we've got, but there's going to be another one over here. So there's going to be an angle like that and an angle like that that we need to figure out. Now, we'll find one of them by using the inverse trig functions. We can look at b, which is inverse sine of 0.7781, or beta rather. Let's clear that, and we want inverse sine of 0.7781. We're in degree mode, and so that gives us 51.0869 degrees. So that's this one right here. This is the one that's approximately 51 degrees. But there's this other one over here. There's this other obtuse angle which can exist in our triangle. Our triangle might be an obtuse triangle which has an angle in it that has a measure of more than 90 degrees. So we also need to consider the possibility that beta is equal to 180 degrees minus this. So that's the other angle that we've got. We've got beta is either 51.0869 degrees or 180 degrees minus 51.0869. because those are the two angles which have a sine of 0.7781. So 128.9131 degrees. So those are our two potential values for beta. Now, at this point, we can't rule either one of them out, and it may be the case that both of them are valid. You're going to tell whether or not both of them are valid in the next step, which is where we figure out gamma. Now, gamma is always going to be equal to 180 degrees minus alpha minus beta. So, at this point, we need to consider two possibilities. So, we'll call the first potential beta here beta 1 and the second beta 2. And we'll continue to label our gammas and our c's in a similar way. So now we're considering two possibilities. Either gamma 1 is equal to 180 degrees minus alpha minus beta 1, or we have gamma 2 equals the other one. We'll handle the beta 1 case first, and then handle the beta 2 case afterwards. So we have that in the first case, we get that gamma 1 is equal to 180 minus 33 degrees minus 51.0869 degrees, which is 180 minus 33 minus 51.0869 gives us 95.9131 degrees, which works out perfectly fine. And so now we can figure out what C1 is. We can use that sine of alpha over A is equal to sine of gamma 1 over C1. Conclude that C1 is going to be equal to A times let's replace each of these with the known quantities. Sine 33 degrees over 7 equals sine of 95.9131 degrees over C1. So from this we can conclude that C1 is equal to 7 times sine of 95.9131 degrees over sine 33 degrees, which we can plug into our calculator and get 7 times sine of 95.9131 divided by sine of 33 degrees, from which we get that C1 is 12.7841. Okay, so that was the case for beta 1. We got our values for gamma 1 and for C1. So that's one of our possibilities. So now let's consider the case where we have beta 2. So we have gamma 2 is equal to 180 minus alpha minus beta 2, which will give us, let me move this up here, which will give us 180 minus, and then alpha was 33, minus beta 2, we got 128.9131, and so we get that gamma 2 will be 18.0869 degrees. So we got a valid value for gamma 2. And so we can get, again, that sine of alpha over A is sine of gamma 2 over C2. And so we can rearrange this and get that C2 is going to be equal to 7 times sine of 18.0869 degrees over sine of 33 degrees. And if we run that, we get 7 times sine of 18.0869 divided by sine of 33, and we get that C2 is equal to 3.9902. So what we get is actually two possible solutions here. We started off with an alpha, an A, and a B, and we found that there were two possible values for beta, each of which giving rise to a possible value of gamma and a possible value of C. This means that there are actually two separate triangles that have the measurements alpha equals 33, A equals 7, and B equals 10. So let's see what the picture is that represents this situation. So similar to before, we can think about trying to construct things by starting with an angle of 33 degrees here, and have a side length of 10, and we're trying to draw a line segment over here with length 7. Now, before when we did this, when alpha was 46 degrees and we had a B of 10 and an A of 7, we found that the other leg here didn't reach. The segment couldn't get far enough. In this case, however, it does get far enough, and in fact, it swings down below the lower side here, which means that there are actually two different triangles that we can form here, two different ways of forming a triangle here corresponding to the two different betas. And in fact, we get beta 1 here and beta 2 here, from which we'll get our gamma 1 and gamma 2, and we've got C1 and C2. So that's where the two different triangles being formed show up here. When you only know one angle and two of the side lengths, if they're the right size in relation to each other, you can actually form two separate triangles satisfying those conditions. Now, there's one more situation that we can encounter that looks a lot like the situation we just did, but that has a little bit of a twist to it. So let's look at the situation. Let's suppose alpha is 12 degrees, A is 22, and B is 20. So going through the same process, we have that sine of alpha over A is sine of beta over B. And so we get that sine of 12 degrees over 22 is equal to sine of beta over 20. Rearranging, we get that sine of beta is equal to 20 times sine of 12 degrees over 22, which we can do in the calculator. And so we get 20 times sine of 12 degrees divided by 22, and we get sine of beta is 0.19. I'll go ahead and just use 2 decimal places for this. I'll use 3. Sorry, I don't want to over approximate things. So we can figure out what beta is here. And again, we're going to get two different possibilities. We're going to have a beta 1 and a beta 2. Our first possibility for beta is just going to be the inverse sine of 0.189, which we can do in the problem. Inverse sine of 0.189 is 10.894. So one possible value for beta is 10.894 degrees. Beta 2 then will be 180 degrees minus that one. So 180 degrees minus 10.894 degrees will give us 169.106 degrees. Now from here we can go through and find gamma 1 and C1 and gamma 2 and C2. Now finding gamma 1 and C1 go just like in the previous case. So I'll move through that. Quickly. Gamma 1 is 180 degrees minus alpha minus beta 1. So that's going to be 180 degrees minus 12 degrees minus 10.894 degrees. And we'll get 157.106 degrees. And therefore, we have that sine of alpha over A is equal to sine of gamma 1 over C1, which gives us that C1 is going to be equal to alpha A, which is 22, times sine of gamma 1. Gamma 1 is 157.106, divided by sine of alpha, and alpha is 12. These are degrees. So we get that C1 is 22 times sine 157.106 divided by sine of 12 degrees. Gives us that C1 is approximately 41.165. All right, and there's one of our possibilities. So now let's look at what happens in the case where we take beta 2. In that case, we'll take gamma 2 is going to be 180 degrees minus alpha minus beta 2, which is going to be 180 degrees minus 12 degrees minus 169.106 degrees. And if we do this in the calculator, we get 180 minus 12 minus 169.106, and we get negative 1.106 degrees. Now, we know how to handle negative angles in a general sense in trigonometry. However, negative angles do not make sense in the context of solving a triangle. It doesn't make sense to say that a triangle has an angle of negative 1.106 or something like this. And so this means that we have no solution here, which means that our beta 2 possibility back here actually doesn't work. Now, this wasn't totally obvious when we first computed them, but as soon as we got to the gamma 2, we saw that it wound up being negative, which means that we don't actually have a solution to the triangle. So these are the 4 possibilities that we can run into when working with a side-side angle situation. Just as a quick illustration of what's going on in this problem, in this problem, we had an angle of 12 degrees. Our B was 20, and our A was 22. So in particular, notice that, let me stretch this out a bit. In particular, notice that our A side over here, which I'm moving around, is actually larger than the B side. So that means that we can construct one triangle out here, which is what we did. But if we try swinging things around and getting a second triangle the way that we did in the third example, then it doesn't actually come back up to meet the horizontal line until way back here. And so that means that if we took this situation, then our original alpha wouldn't be an angle in the triangle, and so it doesn't work. So this is the situation where we get two potential values for beta, but one of them doesn't work because it involves constructing a figure that isn't actually a triangle. So that means that we only have the one situation here that gives us a solution to our problem.